Hi, this is class number 2. Today we will be talking about the relationship of the ideal flow to aerodynamics. But before we do so, let's go ahead and review some of the concepts we discussed last time. So class number 2, ideal gases or ideal flow. Um, so we talked about, let's say we have aerodynamic forces. The aerodynamic forces basically depends the whole aerodynamic forces. There are many physics involved with this phenomena when we study these forces. The physics involve solid mechanics. So solid mechanics, this is more structures. It also involves dynamics. So dynamics, we are talking about the rotation of the aircraft, different rotations of the aircraft. We also had fluid dynamics or fluid mechanics is more general. We can have electromagnetism. And the list can go on and on and on and on and on. So in this course in particular, we are interested in fluid mechanics, I'm sorry. And the fluid mechanics can have many different aspects, and it could have many different aspects. The one that we want to focus mainly on is aerodynamics. Aerodynamics is a subset of fluid mechanics. Okay, and we talked about that this is nothing else than the study is this the aerodynamics is of study of the behavior and interaction of air fluid with solid bodies. Immersed in it. So, as we talked about, nothing else. Let's take our airplane last time. So I got air flowing around this. I want to know the interaction of that airflow, the airflow across the plane, and the solid. That will be the plane itself. That's the type of aerodynamic, um, aerodynamic concept we would talk about in this class. We got an airplane that's moving, so therefore we got flow on top and bottom of this, and we want to know the interaction. Okay, so in a nutshell, this is what we are doing. We want to study aerodynamic forces, but for that we have to go through the subject of physics. That physics involves in so many other concepts, and from the concepts we want to focus on fluid mechanics that go to aerodynamics, and then we study the interaction of the fluid and the solid. Now, just as a review, we talked about this last time, just at least as an introductory level, and we said what is a fluid. We talked about the fluid being a substance uh, that cannot withstand the action of shear forces and will change slope readily under their action. Okay? So given that particular definition of what a fluid is, and we talked about this a little bit last time, we get two different type of fluids. Okay? The fluids can be categorized in two separate parts. Ones are liquids. Liquids, in most parts, they are incompressible. And we talked about that. Basically, what you're saying is if you have a delta pressure, that's not going to cause, that will not cause a change in your delta volume. Okay? In reality, really, you don't have, no liquid is truly compressible, but it's a good assumption. However, gases, as the gases of gases, this is basically air, what we will be talking about in this course, these are compressible. And by compressible, we mean that by a change in your delta pressure, you will get a change in volume. Okay, so this is important to understand that. And that kind of makes sense, right? I want you to think about I got water and I can try to compress that water. I can apply some delta pressure to it, but the fact is that the original volume will be very close to my final volume. There's nowhere the water can go. Now, in the case of air, in the air you can see that as I can take amount of air and put in a container, and if I think about think about a balloon maybe, and if I take the balloon and I blow the balloon, that balloon is going to have a certain amount of air. Now if I make it very cold, I have still the same amount of air in there, the molecules are the same, but they get contracted. And what happens inside the gas itself, you have a lot of interaction between velocity, the position of that velocity, and the energy between one particle and the other. So you have one particle in the gas, you have another particle in the same gas. They're part of the same gas, but they are interacting each other. And this one may have a different velocity, meaning a speed and a direction and a different location than the other particle. And then there is an energy that each one of them can have. And the interaction of the energy also plays in the role. That all that happens in a gas, which makes it a lot more challenging to analyze or even exciting, if you like that term. So to let's write this down. So I just said that gas at the molecular level is a set of molecules with velocity, position, and energy. And all these particles, they which collide with each other. Okay? And then all this also basically leads to also temperature, as I just mentioned for the example of the balloon. The temperature also plays another role into this, and this is a way of storing energy in a gas. Okay, and this is basically known as a, this energy can be in the form of kinetic energy. It can be in the form of potential energy, or it can be in a form of torsional energy. Okay, and so basically think about the following case. Okay, so let's take a container. In that particular container, let's put some gas on it, and let's put a cover on it, and let's put some weight on this particular cover so the gas will remain as it is. So then you're going to have many different particles, all different places. Every particle is going to have its own direction, energy. And what's going to happen in this particle, you got this, and they all go in different direction. And what happens when they collide against the wall? When they are colliding against the wall, they are exchanging the energy that's in the wall as well. This is what we call elastic collisions, based on the principle of momentum. That also has to be conserved. Let me, so for instance, when this is bounced here, right, this particle, let's say I got this particle over here, this particle somehow bounces here, this wall is not going to move. What's going to move this gas is the particle is going to keep moving around. So this interaction with this wall is holding some energy. So when the energy here, this particle jumps to that collision between this wall and this wall actually bounces back. Okay, this is the energy that we are talking about. You can think about maybe a ping pong ball or a racquetball, right? And if you have a ball and you just throw the ball is going to hit here and it's going to bounce back. Okay, so what's going to happen is as this is hitting around, what you don't see is the container moving from back and forth, back and forth. Let's go back to our water bottle here. What happens in bottle water, I got some gas in there, okay? And I can cool this, I can expand this, and somehow you got particles on the inside that are constantly moving. But if the particles are moving, and this is why this container is not moving. This is not moving, this is not bouncing around, although the particles inside there are bouncing around. This is the idea of a gas, of the air. The air inside is moving and doesn't have enough energy to move my container. But however, the energy that my wall has is enough to make my ball bounce back. Okay? So that's basically what we are trying to talk about. We are talking about here. And so let's write this down. When particles collide, against the wall, they exchange energy with it. Okay, and this energy is in the form of elastic collisions. such that the momentum of the system is conserved. Okay, and we know from physics that force is nothing else than rate change, right, with second Newton's law of momentum. So the time rate of change of momentum is equal to force. Now, if I take this and I divide on both sides area, right? I divide this by A and I divide this by A, then I'm going to have pressure, and you have to remember what your mass is. Your mass is nothing else than density times volume. Or, so if I divide this by area on both sides, right, this will come rho times length. So basically what we are saying here, we are saying this is the same thing as rho times length times velocity. Let me put this arrow there so we understand we are speaking with velocity times dt. Okay, so know that my rho can change with time, but my length could change in time, and this can change with time. In the event where my rho and my length does not change, then I could have a case where my equation actually looks something like this. Okay, so this is the equation of momentum. Again, I want to write it down here. Remember the equation of momentum. We are starting with the simple foundation of what my Newton's second law states. Okay, Newton's law. Now, what happens here in this particular case scenario? What happens when the temperature is going up, right? So we know that the temperature we know this equation, right? Where this is pressure, volume, number of particles, of molecules, your constant, your gas constant R, and your temperature. So we know that as the temperature goes up, your pressure has to go up, right? And if my temperature, my pressure goes up or my volume goes up, right? So, or now if I want to keep this completely constant, then what's going to happen is if I take my pressure up, my volume has to go up. And what you can see that this is directly is affecting my equation. See, as my temperature goes up, then my pressure is going to go up, and this is, or my volume is going to go up, and you can see that this equation will be affected. And my pressure is on this side, and so I could just go on this side and say this is the same thing as my nRT divided by volume will also equal to delta T rho L V, the velocity. Okay, so just by so you know that what happens here in this particular equation, this is volume, and as my temperature goes up, this is going to also be affected with time. So this is what this equation is really telling us. Okay, and this equation right here, this equation is nothing else than the equation for ideal gases. So the ideal gas law states the following. For the ideal gas says that your pressure will equal to the density times R times T. And the equations are basically the same. If you look at this equation, I can write P, density is nothing else than mass over volume, RT. So PV is equal to MRT. Okay, so this is nothing else than the mass and the volume. The equations are the same. This equation is only good because for ideal gases, and they follow this equation. So if we assume that our air follows the concept of ideal gases, I want you to think about the following. I want you to think that ideal gases is like the perfect gas in the world. It behaves perfectly the way it's supposed to behave. If you think about the following, if I want the gas to expand, it will expand when I want it to expand, how it's going to expand. But in reality, is a completely more complex equation because it's a time-dependent equation. I can never expect if I'm raising the temperature, I can immediately say the amount of temperature is going to be raised is identical equal to the amount of pressure is going to, the change in my pressure. This is a concept of ideal gases. The perfect gas doesn't have, every molecule in the inside is perfect, is identical, and is behaving the way I would like it to behave. Okay, so in this particular equation, again, P is nothing else than, in this equation, P is nothing else than pressure, and the units of pressure are Nm squared, or pound forces divided by inches squared. Many times we call this PSI, and we may use this as pascals. There are, and rho is the density of the material, of the gas, sorry. Okay, and is the density at the temperature and at the height. Okay, we will talk about that in a minute. And then this is given by kilogram divided by m cubed, and this can be slugs divided by inches cubed. The temperature is, this is temperature, and is given in kelvins or is given in Fahrenheit. Okay, and R is nothing else than universal constant. Let's write that down in the next part. Oh, let's write it down here. So here R is the universal constant. And for air is 287.05. This is Newton meters kilogram Kelvin. Or In English units, it would be 1,716,49. It would be pound force times feet times slug divided by Rankine. Okay, a couple of more things for ideal gases. Ideal gas assumes, just to write it down, assumes the perfect collisions between all molecules and container walls. It says has a negligible molecular interaction and has a negligible volume occupied by the molecule. Okay, just one simple example so we can understand how this really works. Before we move to the example, there's another variation of this equation that's very, very, very important. Um, let's take the equation that we just derived, okay? And let's move, these two are going to be constant, okay? This is not going to necessarily change in my problem. The mass doesn't change and the constant doesn't change. So what I can say is PVT is going to equal to a constant, okay? And what this is saying is if I have the gas at time 1, let's call, and the pressure is equal to pressure 1 times volume 1 divided by T1 has to equal to what happens to my gas at times 2. That's pressure 2 volume 2 divided by time 2. So that means is if I'm looking for any of the quantities and I have enough information on the other side, I can solve for any quantity I'm looking for. Okay. So let's do one or two examples to better understand this concept. I know it's a lot to take probably, and what you have to keep in mind is you have a gas. We talked about an ideal gas, and we said before we move on, we are talking about interaction between air and the structure itself. Before we do that, I told you that we're going to define what we're going to call an ideal gas. The ideal gas has the perfect collision. The molecules are behaving perfectly, and the energy, there's no energy dissipation between the wall and the molecule itself. All that stuff is negligible, and the volume remains unchanged. Given that fact, what we explained today was that PV, pressure times volume, is equal to mass, or sometimes you can express it in terms of molecules, times the gas constants R times T. Okay, the T is the temperature. And then if I wanted to know what my value of my density is, then I can solve the equation for the density. That's the ideal gas. If I wanted to find the real density for my real gas, I can just multiply that by a compressibility factor, Z. So this concludes our whole topic of ideal gas. And we concluded everything with one example explaining how the ideal gas equations actually work. This concludes class number 2.